With innovation come risks. And of course, in the context of Breakthrough Starshot, we discussed for many hours with Yuri in person the various risks involved. As you can see from those diagrams, there are various components to Breakthrough Starshot, and each of them involves risks. But I would like to discuss this in more global terms: innovation and risk, taking the roads not taken. And before I start to discuss this with various examples, I just wanted to make a personal statement. Throughout my career, I was always thinking outside the box. If you look at my papers, I was always trying to think of things that were not discussed by the mainstream. But some of my ideas became mainstream eventually. So I was very glad to see that. And that gave the impression to young people, gave them the illusion that I'm a member of the mainstream establishment. And so I wanted to set it straight. No. The fact that the mainstream adopted some of the ideas is fortunate, but it doesn't identify me as such. But to my dismay, some of my students ended up being mainstream advocates. And by that, I mean they go after the cosmological parameters to a second decimal point, for example. So let me start with Galileo. And Galileo said that in questions of science, the authority of 1,000 people is not worth the humble reasoning of a single individual. This is very deep. It means that each of us has to think about the basic problems on our own. And the methodology that one adapts from this statement is that we should not assume that we know the answer before we actually observe the universe. Many of us make this mistake. We think we know the answer. So let me give you a few examples of innovative future frontiers that are not discussed very often. I just want to give them as several examples. These are not necessarily representative. So I divided them based on the time sequence. So let me start with a long-term, centuries from now. Obviously, the hottest topic would be biology away from the Earth. And by that, I mean life either in the solar system. One can imagine that there might be life under the icy surface of Enceladus, a moon of Saturn. There might be fish in Europa. We might detect lights from spacecrafts. The same project that we are trying to establish with Starshot, sending small probes to other stars, may have been done already by other civilizations. And these things might be flying around. The issue is how to detect them. This is not discussed very often. We often think about searching for life near stars, but if life sent out, intelligent life, sent out probes, it might be easier to find those. We might go after habitable extrasolar and extragalactic planets. And of course, SETI is already part of the breakthrough initiatives. And in the context of SETI, an appropriate approach would be, for example, to imagine in a planetary system, if there are two planets that are co-aligned with the line of sight, there is a better chance of catching a signal because the civilization might have populated both planets. And so one method to approach this is to look at the transiting planetary systems and search for conjunction and try and see if there is any signal during conjunction. And that can be associated with transporting goods between the two planets or communication between the two planets. Another interesting point is, how can you distinguish artificial lights, let's say on a spacecraft, from reflected sunlight? When people look at objects in the Kuiper belt, for example, the assumption is that the light we see is simply reflected sunlight. However, we can tell the difference between artificial light and reflected sunlight. In the case of reflected sunlight, the flux drops as 1 over the distance to the 4th power, because there is 1 over distance squared for the flux impinging on the surface of the object, and then another factor of 1 over distance squared because of its distance from us. And altogether, it's 1 over distance to the 4th. But if a source produces its own light, then the flux would go like 1 over distance squared. So if you watch an object that is moving away or towards you, you can actually tell whether it has it's producing its own light or reflecting sunlight. So that's one approach to figure this out. And just to give you an example for the scale here, if you take the city of Tokyo, it's 31st magnitude in the R band at a distance of 1,000 astronomical units. So that's something that the Hubble Ultra Deep Field could have detected. The Hubble Ultra Deep Field could have detected the city of Tokyo at 1,000 astronomical units. And of course, we often make the assumption that such things should not exist, but humans made the assumption that heavy objects fall faster until Galileo tested it. Other long-term challenges that we might go after in the lab, for example, is producing the inflaton. Everyone talks about inflation as being the correct description of the very early instance in the evolution of the universe. It would be nice to produce it in the lab, or at least find evidence for it. In the very long term, we might build accelerators that perturb the vacuum energy density, the same dark energy that we see in the universe. But in the intermediate time, decades from now, there could be other frontiers that are exciting. For example, we might produce or directly detect the dark matter that fills up the universe. It's quite embarrassing that people are very confident of the standard model of cosmology. And there are orthodox communities of people that advocate the standard cold dark matter with conviction. But we have to admit, we don't know what this matter is. And until we find it, it may be that gravity is modified. So it would be nice to find in the lab evidence for the dark matter. Then, of course, we would like to image extrasolar planets. That would be nice to see if there is evidence for life on them. And the Breakthrough Starshot will aim to do that. Breakthrough Watch will aim to do that. And there are other plans. Then, of course, there is the immediate frontiers that we are all familiar with. Let me mention an example that most of you are not familiar with. The sun, in its future, within 7-8 billion years, will become a white dwarf. A white dwarf is roughly 1% of the size of the sun. It has the size of the Earth. And here comes an opportunity. If you imagine an Earth-like planet passing in front of a white dwarf, it would cover it entirely. So when you talk about transits of a sun-like star, you're talking about blocking maybe 1% of the area of the star, 10 to the minus 4. If you consider an Earth-like planet passing in front of a white dwarf, it blocks everything. So if you're looking for a biomarker, it would be much easier to find it in the atmosphere of an Earth-like planet passing in front of a white dwarf. The habitable zone of a white dwarf is closer in because the white dwarf is smaller. After a few billion years, it has roughly the same surface temperature as the sun, but the area is 10,000 times smaller. So overall, the luminosity is 10,000 times smaller. You have to get closer to the furnace in order to keep yourself warm. And so the habitable zone is 100 times closer to a white dwarf than it is to the sun, roughly at a distance comparable to the radius of the sun. And the orbital time there is roughly 10 hours. So that's a year in that habitable zone. The transit duration is about 2 minutes. So one can look in particular if there happens to be a habitable zone, and don't ask me right now how a planet may have gotten there, but there are ways to get it there. But if it is if there is an atmosphere to the planet, we can look for oxygen with JWST in principle. We can also look for industrial pollution. That's another method to look for extraterrestrial intelligence. Well, not so intelligent, but we are doing it. We pollute our atmosphere with molecules that are not produced naturally. So one can search for those, again, with JWST. And then there are the more mundane, well-known frontiers that are being discussed. For example, imaging a black hole, getting an image of the shadow of a black hole. This is a project called the Event Horizon Telescope that is getting already some data. It involves millimeter wavelength observatories across the Earth and doing very long baseline interferometry at 1 millimeter wavelength. One achieves resolution that is better than a nanoradian that can, in principle, resolve the shadow of the black hole on the background light that is coming from the accreting gas. And there is another frontier that is pursued observationally these days, and that's mapping the hydrogen in the universe using the radio line at 21 centimeter, which is likely to bring data within the next couple of years. The idea is to see those fossil ionized regions produced by the first generation of galaxies in the universe. These were like holes in Swiss cheese that grew with time and eventually overlapped. Now, young people in the audience, and in general, I think this is the elephant in the room whenever you speak to young people. The elephant in the room is, what is the optimal research strategy? Should we be conservative? Should we be daring, innovative? So let me give you several examples in cosmology, specific aspect of astrophysics. I split those opportunities that young people have to 3 categories. One is bonds, just like in the financial market. Bonds are safe investments. So you can think about precision cosmology, measuring cosmological parameters to a better precision. That's a bond. I mean, it's obvious we will get something out of it. You can invest millions of dollars in a project that is well-defined. NSF will be happy about it because you say in advance what you will find. But then you don't discover anything new. You can refine the standard paradigm of lambda CDM. Star formation, I regard that as a bond because we know that stars exist. We know roughly the conditions under which they form. We just need to figure out all the complications. Black hole feedback, also constraints on inflation right now is a bond. There are stocks. These are more speculative ideas. For example, that the equation of state of the dark energy is time-dependent. The simplest case is that it's a cosmological constant. No change in time in the relation between pressure and energy density. But one way to get money out of DOE is to say, maybe it varies. Why don't you find us to figure this out? And a lot of people argue that, and there are projects underway to figure out if indeed the equation of state is redshift dependent. One can search for dark matter, but that assumes a particular type of dark matter. You have to assume whether it's weakly interacting, for example, and then build a whole experiment to detect it. And we had, for example, a conference at Harvard where one of the experimentalists presented his program over the past 2 decades and into the future. So I had a simple question to him. I said, when will you stop? Suppose you continue to put upper limits and you get down 100 times better than the cross-section limits that you have today. When will you stop? And he said, I will never stop. I became very worried about that. He will never stop. So he will get funded, continue to do the experiments, under the assumption that the dark matter is weakly interacting. One can look for annihilation signatures of dark matter, not just searching for it in the lab, but actually looking for its signals as they come from the sky. And then, of course, there are the venture capital investments, the more daring investments. For example, gravity may be modified. Maybe there is no dark matter. We are fooling ourselves. There is no dark energy. It's just that Einstein was wrong. Not wrong, but not, I mean, he was right on some scales, but not on the cosmological scale. People work on anthropic reasoning. That's very popular on this campus. I will not mention names. Some people conjecture there was no Big Bang or inflation. The universe went through cycles. Some people discuss the possibility that the constants of nature vary in time. So these are examples. What I find alarming is that among young people, there is a tendency to invest in bonds. And you may ask why. And was it any different in the past? I think it's more alarming today. And it's driven by job security. There are big communities of astronomers or scientists more generally that work on bonds, and they will likely offer a position for others that work on the same subject. Another aspect of it is that the senior people would like to propagate their own research, and so they tend to cultivate exactly the same type of work among young people. They don't want diversity of ideas. They want everyone to work on their idea. Of course, there is also the aspect that there is a standard model in cosmology. When I was a postdoc, there was no standard model, and so people felt comfortable speculating. Now, because there is a standard model, it's as if you have to subscribe to the dogma. And then there is the aspect of having large groups of people working together. It's just like the corporate world. You have a group of tens or hundreds of people that, if you look at papers that have the number of co-authors bigger than the abstract, that's a good example for such a situation. And then you are part of an agenda that is broader than your own thinking. And under circumstances like that, you tend not to think independently. You are a drop in the bucket. And you think like, together with everyone else, it's very difficult to move big groups to navigate them to go in different directions than they originally planned for. And they usually have very firm schedules. They have to achieve this and that goal within a certain timetable. Now, the history of astronomy, if you just look at the history, it teaches us modesty. Dogmas failed. And the first, of course, was that the Earth is at the center of the universe. So I can understand that. When I look at my daughters when they were very young, they thought that the world centered around them. And our civilization is no different. It took us time to mature. We thought that we are at the center of the universe. Then we realized, no, actually the Earth moves around the sun. Okay, that took some time to figure out. Then it turns out the sun is moving around the center of the galaxy. Also took some time to figure out. Then the galaxy is moving relative to, and then there is no center to the universe. Okay, so problem solved. But we still believe that we are the only life form, at least the only intelligent life form in the universe. Why? Because we don't have any data to counteract that. There would be another Copernican revolution in the context of biology, I think, and that's the fact that we will realize that we are not special, even in that category. It will change religious beliefs of some people, but if that's reality, that's what it is. There was the idea that the universe existed forever. In fact, Einstein liked that idea because he came up with the cosmological constant to make a solution to his equations that would allow for the universe to exist forever, then admitted that it wasn't valid. Another interesting example is there was a committee established by NASA in the early 60s to consider an X-ray satellite. And so very distinguished astronomers sat around the table and reached the conclusion that there is no point in launching a satellite above the atmosphere to observe the X-ray sky. Why? Because we know the sun produces probably X-rays. So there are other stars. They produce X-rays. But who cares? What else can you learn from having an X-ray mission above the atmosphere? Of course, later on, down the road, a decision was made to build an X-ray satellite. I mean, I heard this story from Giacconi. There are many examples that justify the statement that Mark Twain made. He said, "It ain't what you don't know that gets you into trouble. It's what you know for sure that just ain't so." And I wrote actually a commentary in Nature Physics giving 10 examples, and there are many more, to this statement. And they start with Pickering, who was the director of the Harvard College Observatory, my own institution. So here I'm admitting, even there. He claimed that back at around 1910, he claimed that we are done with big telescopes. 50 inches is what you need. And there is no benefit to be gained from building a bigger thing. If you think about ships, it's not clear that a bigger ship can sink a smaller ship. So why build bigger telescopes? That was his argument. There is Cecilia Payne-Kopashkin, another example from my own institution, that wrote her PhD, the first one in astronomy at Harvard, and found out that the sun is made mostly of hydrogen. And then Henry Norris Russell was on her thesis committee. He said, "No, you are wrong. This cannot be the case. We all know that the sun has the same composition as the Earth." So she took it out of the thesis. And here is a lesson for the young people. Don't listen. And then a few years down the line, he wrote a paper saying she was right. So there are many examples of this type. Even just to give you another one more recent, 1992, Piero Madao from Santa Cruz wrote a paper about galaxies at redshifts above 2, talking about their colors. The referee argued that the paper should not be published. Why? Because we all know there are no galaxies above redshift 1, back in 1992. We all know that. There is no point. This is a speculative idea. Let's not publish it. It was not published. Now, why do I address young people? Because young people are more capable of taking the roads not taken. And why? And this is no offense to the older people in the audience. And, okay, I'm not young either. But the younger people, they lack baggage of prejudice. They start their life with a flat prior. They don't assume something. They try to learn. Senior people, in addition to knowing what's right, they are distracted by administrative, fundraising concerns, prefer to protect their reputation. They have something that is very precious. When they look at the mirror, they really like what they see. And therefore, they adopt a conservative approach to doing research with predictable results, like measuring fundamental cosmological parameters to a second decimal point. That's a good approach to get federal funding from NASA and NSF. NASA asks you on a proposal to say what you will discover in year 1, year 2, year 3. Doesn't make any sense. Now, I should say there are caveats to advocating taking risks. Most of the ideas that one comes with, innovative ideas, most of them fail. If you check the numbers, they don't work. But you have to check the numbers. You can't know in advance. Fraction of the ideas, you find like 20 years ago, 30 years ago, someone else discussed them. But in general, the fraction of time that I personally put into innovative research is much more than the fraction of papers that end up being innovative. So that's a downside that one has to take into consideration. There is, of course, the risk of failure, because you're going in an uncharted territory. You don't know if it will succeed. You're taking a risk. You are wasting, quote unquote, some resources in doing so. Time, possibly money. But as people in the venture capital business know, if one of the ideas works, it's highly profitable. It can overcompensate for the lost resources. And that's why it's worth doing. It's not because every time you try it, you will succeed. It's because once in a lifetime, if it succeeds, it's a major, major advance. Now, new ideas are usually accompanied by loneliness, in contrast to the nurturing feedback that one gets by going to conferences where everyone talks about the same thing. And this conference is very unusual in that sense because we are talking about innovation. We will talk about projects that were not done yet, taking roads that were not taken. So this is the very first conference that I have been to in which we are going in a different direction. And that's what I would like to celebrate with this lecture. I'm very happy about that fact. Now, what is the advice that I can give to young people? So let me say a few words about the history. There are ideas that started in the venture capital category, went into stocks, and eventually ended up as bonds. Okay? And a very good example is the Big Bang. Originally, it was speculative. People weren't sure exactly, but we have good evidence that it took place. The cosmic microwave background, Gamow was an outlier. People didn't really pay attention to what he was saying back then. Then Penzias and Wilson, and eventually the current CMB experiments. The dark matter, originally a speculative idea. Zwicky was a person that was not liked by many in the community. Eventually, the data confirmed it. Inflation. When I was a postdoc, I was told, don't touch it. It's speculative. By now, it's the standard paradigm. So there are these examples, but there are also examples where a venture capital idea goes into the junk. Okay? And one example is the alternative to the Big Bang theory, which was promoted at the time by the most prominent astronomers, people like Hoyle, Bondi. You can find their names in many other contexts. However, they were wrong. And the ultimate verdict comes from data. And you have to accept that. The problem is some people don't accept data. There was the idea of topological defects being responsible for the structure in the universe, the large-scale structure, which turned out not to be the case. The idea that dark matter is baryonic, ordinary matter. That was popular among people like Jim Peebles. And then there was the macho experiment and microwave background isotropies that ruled it out. And then the idea that the X-ray background, for example, is coming from a hot intergalactic medium. There was even a tantalizing piece of evidence in favor of it that went away. Turned out to be the exhaust of the experiment, of the rocket. So there are these tracks. You can start with a venture capital idea and end up in the wastebasket. However, some of those ideas end up becoming stocks. Some of the stocks may end up in the wastebasket. But eventually, there are some ideas that tend to become bonds. And a common investment strategy among postdocs is to put, and here I have very rough estimates based on the people I meet in the corridor, okay, all the postdocs that surround me. They typically put 5% in venture capital, 5% of their time or research effort, 15% in stocks, and 80% in bonds. And I mentioned before why I think that's the case. My recommended strategy is 20% in venture capital, 30% in stocks, 50% in bond. Another thing to be worried about is the connection to reality, okay? So when you think about the financial world, for example, housing, okay? Housing, if you look at a house, there is something material in front of you. There are hard facts. You know, you can see how many rooms, what is the square footage. There are some hard facts. But the question is, what's the price? Okay? And the same, you can find an analogy between that situation and physics in the sense that we have some data on the world. There are some theoretical ideas. But there are also some theoretical ideas that have no data to support them. So what value do we assign to them? Should we work on string theory? These are intellectual assets. What is the value of an intellectual asset if it doesn't have backing from data? And the worry is that just like the housing market ended up with a bubble, that if you work on something that has no contact with data, you will end up with a theory bubble. And so this is my definition of a theory bubble. It's a long period of time of stagnation during which talented physicists invest time and efforts in an idea that has no actual value in describing nature because there was no experimental test that could check it. So let me conclude with some rules and some consequences. First of all, for the young people in the audience, beware of theory bubbles that have no foreseeable contact with experimental tests. It's very important to check your ideas against data because nature is more imaginative than we are, very often. Also, don't work on ideas that are second order in speculation. It's a speculation on top of a speculation. Like if you believe in modified gravity, adding hot dark matter to that so that it will agree with data is not a good idea. Keep in mind that the number of theories is much greater, or it's basically infinite, unlimited, compared to the one truth that we're trying to seek. And also, progress is not linear in time. You may work for a long time without having a clear idea, and then suddenly at the end, something will click. So even though you put a lot of time and effort into something, don't worry about it. What matters is the one thing that clicks. So the conclusions. The breakthrough initiatives are extremely important because they add innovation and risk-taking to the mainstream of astronomy. Senior people should find strategies to reward innovation and risk-taking among young researchers. That's very important because that will reinforce work by the young people in these fields. And of course, funding agencies need to nurture scientific discoveries by allocating some fraction of their funds to venture capital investments, not put everything under bonds. And for those that take the roads not taken, keep your spirits up. I don't see any other reason for doing science than actually going in directions that others did not explore. And I'm trying to encourage that in my group of postdocs and students, some of whom are here in the audience. This is a picture of a tree in my backyard. And you can see one of the branches has an insulation tape around it. When we came to the house, this branch almost fell apart because it was broken. And the gardener said, "Why don't you just cut it off?" I said, "No, I will put an insulation band around it. 10 years down the road, when I look at it, there is a huge, tall branch coming out of it right now." And I kept the insulation tape as a testimony for that. And my lesson is that young people that are worried, not sure, they are in a very fragile situation in their career. You need to nurture them, give them confidence, and they will go far above the level of your eyesight. That's my lesson from this branch. And finally, let me quote this well-known poem by Robert Frost, who lived not far from where I live. I live in Lexington, Massachusetts. He said, "Two roads diverged in a wood, and I took the one less traveled by, and that has made all the difference." Thank you. Shall we take questions?
We have time for one or two. So.
Okay. Questions? Phil.
Avi, great speech, thank you. How do we convince the National Proposal Foundation, that's called the National Science Foundation, to sort of unshackle researchers from the kind of servitude of writing a proposal, which now has an acceptance rate of roughly 1 in 10.
Yes.
So most people waste their time writing proposals rather than doing science.
This is an excellent, the question that Phil asked was what should be the advice to the NSF, for example? And I would recommend something that is already done in Europe, which is to provide funds to individual researchers, not to projects. What NSF does most of the time, I know there are exceptions, it gives funds for a project that maybe lasts 3 years, but that's it. A better approach is for people that have a track record of demonstrating creativity and success, provide them with the funds to do their research because you give them trust. You think that they can do something useful. And that will guarantee stability in their approach to how to attack problems instead of focusing on something that would sound like it is straight in the mainstream so that the reviewers will accept it. And then you have to propose it again and again. If you have the confidence that you're given legitimacy to go along a path that you believe is the right one without being scrutinized for an extended period of time, I think that is a key to innovation.